For our first example, we got right here, example 1, we have a stone falls from us to earth, estimate the instantaneous velocity at t equals 0.8 seconds. So we're going to use this average velocity formula here, and in this average velocity formula, we're going to use this s of t equals 4.9 t squared seconds. We're going to use that for the s of t's that are in the top of this formula for this particular problem. So we want to drop a stone and then say when it's 0.8 seconds after you've dropped it, what's the instantaneous velocity at that point? So we don't have an instantaneous velocity equation, but what we're going to do is we're going to look at the average velocity and look at the average velocity over smaller and smaller time intervals. And as we get time intervals that are very, very close to 0.8 seconds, hopefully we will see good things happen, and we will get an estimate on what the average velocity actually is. So, and we'll try to get it to let's look for an accuracy of 3 decimal places. So to start out, let's write down our average velocity formula with the 4.9 t squared plugged in. So we have t1, so we would have s of t1 would be 4.9 times t1 squared minus s of t0 would be 4.9 times t0 squared. And then that's all over t1 minus t0. So what I'm going to do is I'm going to look at some intervals, like, since we're looking at 0.8 seconds here, I'm going to start my intervals at 0.8 seconds, and let's look at 0.8 second out to 0.81 seconds. So that's going to be the average velocity from 0.8 to 0.81. So it's the average velocity of 1/100th of a second starting at 0.8. So we start at 0.8, we look 1/100th of a second further, and whoops, no, that, yeah, 100th of a second further, and we say, okay, that is, we're going to find the average velocity over that. And that'll probably be, you know, relatively accurate, but we'll say, what if we looked at closer times? So maybe 0.8005. And then, so we looked at an even smaller time segment. That would be, these two numbers would be, this number here would be closer to 0.8 than 0.81. So this is over a much smaller time segment. So we should get, our average velocity should be closer to the true instantaneous velocity. And we'll look at like a third one with even more zeros, maybe 4 or 5 zeros. Say 4 zeros. So these will be our 3 time intervals we'll take a look at. And then we'll see what our average velocities are and see if after these 3 time intervals, if it's settled down. And if it hasn't, we could look at it one with even more zeros, like maybe 6 or 7 or something. So the point is, the t-zeros in these are all 0.8s. What I'm going to do is I'm going to try to create an equation that I can type into my calculator in the y1 equals in my calculator. I'm going to use calculator notation here. So we would put in 4.9 times the variable x in your calculator squared minus 4.9 times, here's where I put our 0.8 squared. And then that'll all be over x minus 0.8. And if I have this equation, then what I can do is I can go to the table. I can change the independent variable to ask, and then I can type in these numbers here for my t1 values, and this equation will tell me the average velocity. So I'm going to put little arrows beside this where I can type out the average velocity numbers we get back from that. So let me type this into my calculator. I hit Y1, I clear everything out there. I put 4.9 x squared minus 4.9 times 0.8 squared. Whoops, I've already made a mistake. Okay, 4.9 times 0.8 squared. Then that's all divided by, make sure you use parentheses around the top and the bottom so that, you know, like when you type it in, you put parentheses around the stuff so you make sure your division's going through exactly how you want it. We get x minus 0.8. And now I go to, I hit second table set. So second, or it's the second in the window button. It'll say in blue above it, table set. See if I can show you in the little video right here. It's this button right here. When I hit that, I get a screen that looks like this. And this is where I want the independent value set to ask to be. So you set the independent value, it's under the second Windows button. You just write that out here. So you hit the second button. And then you also hit the window button. And that'll let you get into here where you can change the independent variable to ask. Then you'll hit second table, and you'll be able to type the numbers in. So I'll type in 0.81. And that gives me back, let me hover over it so I can see exactly, gives me back 7.889. So let's type in 0.8005. That gives me back 7.8425. Let me put in a 0.00 or 8 4 zeros and a 1. That gives me back 7.840049. And I said I wanted to do this out to three decimals of accuracy. So basically what I'm looking for, like this thing's definitely 7 because all these values here agree at 7. It's 7.8. This one here started out as 0.88, but then this one became 4, and we saw another 4. So we know we got it to 2 degrees of accuracy. It looks like it's 7.84. But the third decimal place hasn't settled down yet. Like here it's 2, here it went down to 0. I'm going to take one reading that's a little bit closer. So I'll use 5 zeros and maybe a 5 and see what that one gives me back. So we get 0.8, 1, 2, 3, 4, 5. And that gives me back 7.84, 3 zeros and a 2, 4. So at this point, 7s have settled down. The 0.8 has settled down. The 4 is there. And now we got the 0 settling down as well. So we'll say the instantaneous velocity is about, we'll say 7.840, and our units are meters per second. So we looked at the average velocity over smaller and smaller time intervals, and the closer the time interval is to the value that we want the instantaneous velocity at, the closer the average velocity value will be. So we just take the average velocity and we kind of just look at average velocity where the interval is fixed at the number that we want, and the other interval we let it get closer and closer and closer to the value we're looking at, and then the average velocities of those shrinking time intervals will converge to the instantaneous velocity like we can see in this case. So that's our first example.